Okay, I apologize in advance, but this is probably the hardest lecture that you're going to do. You have to not take a leap of faith, because I explain how this is true and how we can do it. Some people have a really hard time wrapping their head around it. Today we are going to learn method of sections. Now, up until now, we figured out that we could figure out all the loads on a building or an object, and we know we can narrow it down and find the specific kind of smaller loads that act on an object. We now know that we can use summing the forces in the y direction, the x direction, and spinning about z, needing to be 0 to ensure it's in static equilibrium, to figure out what reactions are required to make that true. But, like I said last week, if we have a load right here, we know we can figure out what reactions we need at the end to keep this from moving. But what's not clear is, how does this load move through this object always over to these reactions? And that is what we're going to talk about today. So that's the goal of today's lecture. I find it easier to work with axial loads first, which means we're going to talk about trusses today. The method we learn today, we're going to be able to do with beams and columns as well. But today we're going to talk about frames, and so frames only have axial loads in them, or at least the ones we're going to analyze are only going to have axial loads in them. So first I'm going to give a refresher of the images we learned last week that show how we talk about these free body diagrams. Remember, a free body diagram is a simplified drawing of the object we're talking about that shows all of the loads and moments acting on it and where they're located, and all of the reactions acting on it to keep it from moving and where they're located. So let's take a look. So last week we talked about coordinates. So we know y is up, x is back and forth, and z is in and out of the page. If we're talking about 2 dimensions, which is what we often do, we're talking about the xy plane, and we know that we're talking about spinning about the z-axis. We learned about the right-hand rule, where if we want to talk about whether something is positive or negative spinning about the z-axis, we curl our fingers in the direction it's going, and our thumb will tell us if it's positive or negative. If we're curling our fingers in the direction it's trying to spin, if our thumb is coming out of the page, that means we're talking about a positive moment. If our thumb is acting into the page, we're talking about a negative moment. We'll often use uniformly distributed loads when we're talking about beams, and that's going to be really important next week because it's the most common type of loading we see on a beam. We looked at reactions and how we draw them, and we knew that there were 3 different major types of reactions. A pin, or a roller, depending on what direction we allowed it to roll, or a fixed connection, where we didn't allow it to translate in either direction or rotate. We don't often, or we try not to use moment connections if we don't have to, because they're expensive and hard to build. We can use them, and I will show you next week examples where we actually do use them. If we're drawing something on a piece of paper, if you see a little gap between the 2 elements, we're talking about a pin connection, unless we draw this big dark triangle filled in, and that means we're moment connecting those 2 things. So moment would have to go in between those 2 things. To be statically determinate, we're saying there must be a restraint or restraints that stop it from moving in the y direction, stop it from moving in the x direction, and stop it from spinning about the z-axis. A common free body diagram we might see is a beam with a uniformly distributed load, a simply supported beam with a uniformly distributed load. This reaction means that it can't go up and down or back and forth, and this reaction means it can't go up and down. I showed you how basic detailing results in this situation for steel most of the time. Next term, we're going to talk about how if it's a concrete beam, we actually end up inherently with moment connections at the end, but that's way beyond the scope of what we're going to talk about, but it is something I'll introduce to you near the end of structures 2. But for now, we're probably going to be talking about simply supported beams, so a pin roller condition with a uniformly distributed load. So that's great for everything happening to our object. But what we want to know is what's happening if this is where our load is applied and this is where our reaction is. We want to know what's happening in here. So if we draw internal forces, if they're pointing towards the spot we're cutting or the dot or area that we're cutting, they are in compression. If they're pointing away, they're in tension. So if we, for example, we're talking about this point right here, that arrow is pointing to that dot, so that would be compression. This arrow is pointing away from that dot, so we're saying tension. So this object would be in tension, and this object would be in compression. If we made the dot right here, or we cut in that member, if we drew the arrow towards the dot, it would be compression. And same thing here, if this was the dot and we drew the arrows away from the dot, it would be in tension. So these are implied forces at a joint or a member. Now last week we talked about this, we talked about solving for the reactions, figuring out what it takes for our object not to move up and down and back and forth and spin about the z-axis. So most of the rest of this lecture, I'm going to now do pointing down, facing at the calculations sheet. I'll talk a little bit in between, but I don't think I'll stop and turn it back to my face just because most of this lecture is all about recording calculations. I do want to quickly go back. No, we're going to flip down and we're going to focus on doing the calculations. I might change my mind when we introduce method of sections, but I think I can do it fairly easily while we're talking about it looking at the paper. So here we have a truss with a load of 100 kilonewtons coming down at this point right here. And they've drawn the pin roller reactions for us. So there's something stopping this end from going up and down and back and forth, and this end from going up and down. They've given us the dimensions, so we should be able to solve this for the reactions. I always like to, as I've said, draw everything out again, just so it's handy right there on the paper for myself. So let's draw out this truss that we've got. So we have a truss that is 3 meters tall. And every 2 meters there were webs or bays and with web elements inside it. So we've got our top chord, our bottom chord, and all of the web elements within it. There was a force of 100 kilonewtons applied at that point there. Let's draw our dimensions in here. 3 meters, and they said that each bay was 2 meters. So 2 meters, 2 meters, 2 meters, and 2 meters. And it's a pin roller connection. So this is reaction left, reaction X, and reaction right. We know that we want to figure out what these reactions need to be to stop this truss from moving up and down, back and forth, and from spinning about the z-axis. We know that we can, if this thing isn't spinning, it means it's not spinning about any point, which means we can pick whatever point we want to pretend to spin this about. So we want to know what it takes for the sum of all the forces in the x direction to be 0, and if we say that's positive and that's negative. Well, all we've got is our x. There's nothing else in the x direction. So our x equals 0. We can sum the moments about the z-axis, where everything going in that direction is positive, or curling my fingers in that direction, meaning my thumb comes out of the page. What it takes for summing the moments about z to be 0, and I'm lazy, and I often always pick this left-hand point right here. I often pick this point right here. Well, to be a moment, you need a force with a distance. Our L passes right through that point, so there's no distance from it, which means it doesn't try to make it spin about that point. It tries to make it move, but it doesn't try to make it spin. Rx, same thing. Rx passes right through the point, so it's not trying to make the object spin. Our 100 kilonewton force, imagine I'm putting a thumbtack right here, it is trying to make the object spin about that point. So we can see that it's trying to make it spin in that direction. So if I curl my fingers in the direction it's trying to make it spin, the direction my thumb points tells me if it's positive or negative. My thumb is pointing into the page, which means this 100 kilonewtons is spinning it in the negative direction, or minus 100 times we need a force with a distance to cause moment, or force times eccentricity. This 100 kilonewton force is 2, 4, 6 meters away from this point right here, or 100 times 6. We also have this reaction at the right end here that tries to make the object spin about this point. If I push the page in the direction of that force, it's trying to make it spin in that direction. If I curl my fingers in the direction RR is trying to make it spin, my thumb is pointing out of the page, which is the positive direction. To be a moment, you need a force and an eccentricity. So RR is 2, 4, 6, 8 meters away. Now, what do you think? Do you think the force is going to be higher here or here? Do you guys even have intuitive guesses about what percentage you think is going to go where? I purposely made this one divided into quarters to see if you could intuitively guess what these answers are going to be. So hold that in your head. Take a guess about what you think these values are going to be. Now let's plug in the math to solve for RR. We bring this over here and make it positive and divide by 8, or 100 times 6 divided by 8. RR equals 75 kilonewtons. Or it is 3/4 of the force. RR is 3/4 of the force. Look at this. This is 3/4 of the way over across the beam. So that seems kind of interesting. We have another equation. We still haven't solved for RL. We can sum the forces in the y direction. The y direction where everything upwards is positive. And we want to know what it takes for this object not to move up and down. Well, we have 100 kilonewtons pointing downwards, so minus 100. We have RL going upwards, and we have RR going upwards, but we've already solved for RR. plus 75. We can rearrange this, and we get RL equals 25 kilonewtons. So we can come back up here if we would like and actually write that in. 25 kilonewtons, 75 kilonewtons, and that equals 0. So we've solved for our reactions. That's what we've figured out how to do so far. But it doesn't tell us what the forces are. This is somehow getting from here all the way over to here. We can imagine that some of the force goes in all of these members. So something's got to be going in here and here and here and here. But we have no idea what that is. But we know that somehow 75 kilonewtons of this 100 kilonewtons gets over here. And somehow 25 kilonewtons of this 100 kilonewtons gets over here. And we need to figure out how that happens. All right, here is how method of sections works. We've already established, and we did this by hand calculations with our teeter-totter example last week, that if this object isn't spinning about this point, it's not spinning about that point, nor is it spinning about that point. If we've proven that this thing can't spin, it can't be spinning about any point. Well, that is the same, or that holds true for any section of this. So if we've looked at this truss here with this load on it, what if we said, what if we cut this truss, or pretended we were cutting this truss right through here, or right through here? And we only looked at one side of the truss. We know that this portion of the truss is not moving up and down, sliding back and forth, or spinning about a point, because the object isn't doing those things. So if we make a cut right here, there must be something happening in these members to stop this section from moving up and down, sliding back and forth, or spinning about the z-axis. So this is where I said for some people this is a bit of a leap of faith, but for some of you, you just find it very, very obvious what I'm saying. Of course, if this thing isn't moving, a part of it can't be moving either. And this is where we get the name method of sections. So what we're going to do is cut this truss, or put an imaginary cut in this truss right here. We know that this truss as a whole isn't moving. And so when I say moving from now on, I'm talking about moving up and down in y, back and forth in x, and spinning about z. So if this object isn't moving, and I pretend that this half of the truss isn't here, I know that this isn't moving either, because something is holding it in place. What's holding it in place is this half of the truss, but something within that half of the truss is holding it in place. Just want to see what slide I have next. Okay, so to be in equilibrium, every part needs to be in equilibrium. So if I make this cut right here, the rest of the truss is still there. It hasn't disappeared. It's what's holding it in place. But we know that there must be a force in these members that's holding it in place. So we can say, the same way we did with the reactions, we didn't know what the values were, but something was holding that thing in place. Well, we're going to say there's some unknown internal forces holding this part of the truss in place. For this particular example, I'm going to call it A, B, and C. We're going to see that we can call it whatever we wanted. Now, this is where understanding if something is positive or negative versus tension or compression is very important. I have drawn all of these as a tension force. If you remember back when I talked about a few slides ago, If you have a point and an arrow is pointing away from the point you've cut, it is tension. If it's pointing towards it, it's compression. So I've drawn this force pointing away from the cut. I've drawn this force pointing away from its cut. I've drawn this force pointing away from its cut. I've drawn them all in tension. But look, B is partly pointing downwards and partly pointing this way. Downwards is negative. So tension does not mean negative or positive. If we guessed wrong, remember, I just guessed that these would all be in tension. That seems a little far-fetched to me that they'd all be in tension, especially considering we have talked about elements in bending. Tops are often in compression and bottoms are often in tension. So it would be surprising to me if all of these actually were in tension. If I solve for A or B or C and I get a negative number, it tells me that I drew my arrow wrong. So it's going to be very important that we track whether our things are in tension or compression as we solve for them. So let's find the internal forces for A, B, and C. So we're going to make a cut through right here. We're going to make a cut through right here, and we want to solve for those internal forces. Okay. Cut. Keeping left side. So let's draw this out. So this is where we're making our cut. We know that this bay was 2 meters. We know that this dimension is 3 meters. And we know that there were reactions acting on this. This was 25 kilonewtons, and this was 0 kilonewtons. Now, people always say, how can you do this? You don't have your force applied to this section. Well, here's the thing. This 25 kilonewtons is only true because there's a 100 kilonewton force applied right there at that point. If this 100 kilonewtons was at a different spot, this wouldn't be 25 kilonewtons. If this force wasn't 100, this reaction wouldn't be 25 kilonewtons. So this is dependent on the fact that this is a 100 kilonewton force applied at that location right there. We have unknown internal forces acting on this. So we're going to draw some placeholders here. I'm going to draw all of these forces, internal forces, as if they were acting in tension. And I'm going to call this one A, and I'm going to call this one B, and I'm going to call this one C. But I don't know what they are. I don't even know if they're in tension or not. I'm making an assumption here that they are. Now, we know that this object isn't moving up and down, or back and forth, or spinning about the z-axis, because the object that it's taken from, or the section part that it's cut from, isn't moving up and down, or sliding back and forth, or spinning in space. So these have to be keeping it in equilibrium. That means the sum of all the forces for this section moving up and down have to be 0. The sum of all the forces for this section sliding back and forth have to be 0. And the sum of the moments about the z-axis have to be 0. Now we know that it's really easy to work with things in the principal axes. A is nice, it's working in the x-axis. C is nice, it's working in the x-axis. B is a bit of a pain because it's on the diagonal. Our 25 kilonewton reaction is up and down, and our 0 kilonewtons is in the x-axis. So it seems like it might be handy if we knew what B was broken down into its x and y components. Or what if we looked at a small version of B? Let's look at our similar triangles here. If this was B, this would be BY, and this would be BX. Remember, we've got the sum of the squares, the square root of the sum of the squares here. This is a right angle triangle, and that is an angle. How could we figure out what that angle is? Well, we know that these forces are following the same triangle as our dimensions. If this is 2 meters and this is 3 meters, we can figure out what that angle is. So that angle, which is right here relative to the x-axis, remember I'm lazy. I always like to do this relative to the x-axis. The 3 meters is opposite, the 2 meters is adjacent. If we have opposite and adjacent, we often like to use tangent. The tangent of the angle is equal to the opposite side divided by the adjacent side. Or our angle that we're looking for is the inverse tangent of opposite, which is 3 meters, divided by our adjacent side, which is 2 meters. We now have an angle of, I'm going to check that my calculator's in degrees. It is. I'm going to use the inverse tangent of 3 divided by 2, and I get an angle of 56.31 degrees. Well, now I know what this angle is. I have B. I can figure out what BY and BX are. BY is the opposite side. I know what my hypotenuse is because I know that B is what I'm working with here. I could write B in relation to BX and BY. So B is my hypotenuse side, BY is my opposite side. When we're talking about opposite, so it's SOHCAHTOA. So opposite is sine. We know that sorry, just 1 second here. We know that the sine of the angle equals opposite over hypotenuse, and we know that the cosine of the angle equals adjacent over hypotenuse. Well, our hypotenuse is B, our opposite is BY, and our adjacent is BX. We can write this out. Sorry, I just want to make sure I'm doing something consistently here for you guys. Yeah, okay. So we can write this out, but what we want to know is what BY and BX are. Well, BY is the opposite side. BY, or opposite, is going to equal the sine of the angle times our hypotenuse. Our hypotenuse is B, and we have sine of 56.31 degrees. BX is going to be B times the cosine of 56.31 degrees. So now we have BY written as, we have B written as Bx, and By, that might make life a little bit easier when we're summing our forces up. Okay, let's try using those equations that we know. Summing the forces in the y direction, summing the forces in the x direction, and trying to spin about a point. Let's start by doing what we always do, summing the forces in the x direction, or the order we've done it in most of the time. I'm going to show you that depending on what we're doing, changing the order up might make life a little bit easier, but you don't have to. You can do this in whatever order you want to. We want to know what it takes for the sum of the forces in the x direction to be 0. Well, we've got our 0 kilonewtons going in that direction. We've got A going in that direction, which is positive. We've got C going in that direction, which is positive. And we've got Bx going in that direction, which is positive. Bx is B cosine 56.31. So that's just Bx written here because Bx equals B cosine 56.1. Those are the only things working in the y direction, and we want to know what it takes to equal 0. Well, we have 3 unknowns and nothing else. So that doesn't seem like it's going to help us very much. But we still have 2 more equations. Maybe we can start to figure something out. Let's next step sum the forces in the y direction, where everything upwards is positive. We've got our reaction of 25 kilonewtons going upwards, and the only other thing is By, which is going downwards, which means it's a negative. So By equals B sine 56.31 degrees. Those are the only 2 forces acting in the y direction. Well, look at that. 1 equation, 1 unknown. It looks like we can solve for B. So we could bring this over to the other side and divide 25 by the sine of 56.31, and we can solve for B. Or 25 divided by the sine of 56.31, and we get that B equals 30.0 kilonewtons. So my answer here is a positive answer. I guessed that B was in tension, just because it's easy to draw everything as if it was in tension when we don't know what it is. I guessed that it was in tension. My answer is positive. So that looks like I was indeed in tension. I always like to write this here so that the next person coming and looking at this can see very easily and very handily that it is in fact in tension. And remember, you're going to be doing part 2 of your project where you're going to go through these steps for a truss, and it would be very handy for me to give you points if I could see at a glance that you understood that that was in tension. So we have one thing solved for, and we could plug this back in here, but we'd still have 2 unknowns. Maybe we should make use of our 3rd equation. Now let's sum the moments about the z-axis where everything spinning in that direction is positive. We want to know what it takes for this to be in equilibrium, for the sum of those moments to be 0. And I'm going to pick that point right there. I'm going to pick reaction L, or my left reaction, to spin about. So I'm going to imagine that the thumbtack is right here, causing this thing to spin. All right. I have my 25 kilonewtons acting through it, and my 0 kilonewtons acting through it. So neither of those cause it to spin. C passes directly through my node, so it doesn't cause it to spin. A is acting along this line right here. If I put a thumbtack right here and pushed at A, it tries to make my paper spin in this direction. I can curve my right hand in that direction, and if I point my thumb, it's pointing down into the page, so it is negative. So I have minus A, and then the closest this force acts along the plane to my point that I'm trying to spin about is my distance. So A is acting along this plane right here, so the closest it comes is 3 meters. I have B passing along this plane. I could figure out exactly how far away B passes from this point, but that would be a bit of a pain. I've broken BY and BX out. Now remember, I've just happened to draw this at the midpoint. I could have drawn this section right here, right as close to this line as I possibly could. Nothing new is happening in there. So essentially what I'm saying is that BY is happening here and BX is happening right here. If I put my thumbtack right here and push right here, BY is causing the paper to spin in that direction. Or if I curl my fingers, BY is causing it to spin like that, point my thumb down, it's negative. I've got minus BY times, and BY, the closest BY comes, it's acting on this plane right here, the closest it comes is 2 meters. BX, I know we've drawn it right here, but we could have drawn this cut right here at this point, as close to that node as possible. We're essentially talking about what's happening right there. BX then is trying to make it spin in that direction. Put my thumb down. It is also in the negative direction. And it is 3 meters away. And we want to know what it takes for the sum of all of those to be 0. Well, we have minus 3A minus, well, BY we know is B sine 56.3, and we know that B is 30. So 30 times sine 56.3 times 2 minus BX. Well, BX is B cosine 56.31, and we know that B is 30. So 30 times the cos of 56.31 times 3. We can plug some of these in. We've got minus 3A minus 30 times the sine of 56.3 times 2 plus 30 cosine 56.31 times 3, or minus 99.84 equals 0. So A equals, so we bring this over and it becomes a positive number, but then we're dividing by minus 3. And we get A equals minus 33.3 kilonewtons. Well, we have a negative number. We know that the value is 33.3. I guessed that A was in tension, but this negative number implies that I guessed wrong. So what we're really saying is A equals 33.3 kilonewtons in compression. So that A is actually a compressive force. Well, that makes sense. We've been talking about things in bending where the top is in compression and the bottom is in tension. It makes sense then that this might be in compression and this might be in tension. I would recommend that you still always draw things in tension though. The reason I always like to draw things in tension, that means that if I get a negative number, I know it always means compression because it means I guessed wrong. If I drew some things in tension and some things in compression as guesses, I would have to stop and look at what I drew each time to know if my answer meant it was tension or compression. Doing it this way, by default, a positive answer will always be tension because I guessed right, and a negative answer will always be compression because I guessed wrong. So we know that B equals 30 kilonewtons in tension, and that A equals 33.3 kilonewtons in compression, but we still don't know what C equals. So we can come up here and plug these things back into this. In this, I was still drawing A in the positive direction, and I know it's now minus 33.3. So I've got minus 33.3 plus C, which is my unknown, plus B, which I know is 30, times the cosine of 56.31 degrees equals 0. I can rearrange this and solve for C. I can bring this over here and it's negative, and bring that over there and it's positive, and I should be able to solve for C. Or negative 30 times the cosine of 56.31 plus 33.3 equals C equals 16.66 kilonewtons. The answer is a positive, so that means it's in tension. It means I guessed right. Well, that makes sense that the bottom chord should be in tension, so it seems like I'm on the right track. Now, here's where so many people say, I don't get it. Why did you keep this side? We made an imaginary cut right here. Why did you keep this side? Well, what I'm going to do is I'm going to do the same thing, and I'm going to make my cut here, but this time I'm going to keep the right-hand side. So this time I kept the left-hand side. This time I'm going to do it keeping the right-hand side. And I want to know, do I get the same answers? Doing it this way, I got that A equaled 33.3 kilonewtons in compression, B equals 30 kilonewtons in tension, and C equals 16.6 kilonewtons in tension. I want to know, does it matter which side I keep? Now, what do you think? Just take a guess. Do you think I'd be going through all this if you just couldn't just do it however way you wanted? It doesn't matter. We're going to prove that it doesn't matter if you keep the left-hand side or the right-hand side. If you do method of sections, as long as you're consistent, you'll get the same answers. So let's do this keeping this side of our truss. So it's the same truss, but I'm going to make the cut right through here, and I'm going to keep this side of my truss. We know that this is 3 meters right here. And that's 2 meters. And that's 2 meters. And we know that this part of our section had some things happening to it. We have a reaction of 75 kilonewtons. We calculated that. We also know that there is 100 kilonewtons acting on it right there. And for this section not to be sliding back and forth, or moving up and down, or spinning in space, the other half of the object must be holding it in place. That means there must be internal forces here that stop it from moving. We don't know what those internal forces are, and I, being lazy, always like to draw those unknown forces as if they were in tension. So I'm going to draw them all in tension, and then I'm going to calculate to see what the values are. If I get a negative number, I'll know I was wrong. One thing that's nice is we've already figured out what these angles are. Remember over here, we had already figured out this relationship? Well, this still holds true. Look, we've still got the same 2 meter by 3 meter dimension here, and that means we're still going to have the same angle, which means that this triangle will be true. It'll look a little bit different because the arrows will go in different directions. But this is B, this is BY, and this is BX, and that's an angle of 56.31 degrees. So that means still, if we go through all this, we see that BY equals B sine 56.31 degrees, and BX equals B cos 56.31 degrees. So at least that step we've already done. Now we can start to think about this object and all of the directions it could move. We don't want it to move up and down, we don't want it to move back and forth, and we don't want it to spin about the z-axis. And we know it's not because we've already found that the reactions for the whole mean it's not. That means there are internal forces that make this portion not move relative to this portion. So we can start to calculate those. I am going to try doing it in an order that I think might make life a little bit easier, only because I'm a little bit experienced about it at this. Let's draw these in. That's our BX, and that's our BY. Remember last time we started summing it in the x direction, and we had an unknown of A, an unknown of BX, and an unknown of C, and then we had to go solve everything else and come back? Well, I'm just looking at this at a glance, and it looks like the only unknown up and down has one unknown. I'm going to start summing my forces in the BY. It does not matter what order you do these in. Sorry, I'm going to sum my forces in the y direction, and I want to know what it takes for the sum of all the forces in the y direction to be 0. Or I want to know what is making this thing not move. I have 75 kilonewtons acting upwards. I have 100 kilonewtons acting downwards. And I have BY pointing upwards. Well, BY is B sine 56.3. So plus B sine 56.31 degrees. Remember, this is just BY. I just went right ahead and substituted it in right away. And I want to know what it takes for the sum of the forces in the y direction to be 0. So I can sum all of these up, move this over to this side, and then divide by the sine of 56.31. So I bring 100 over, and it becomes positive. Bring my 75 over, and it becomes negative. And I divide by the sine of 56.31 degrees. and I get B equals 30.0 kilonewtons. I guessed that B was in tension. My answer is positive. That means I guessed right. So we have the exact same B value that we calculated by cutting and keeping the other section. Let's keep going with this and see if we get the other numbers the same. Let's sum the moments about the z-axis. And I am going to do another lazy thing here. Remember, if a force passes through a node, it doesn't have a moment associated with it. I could spin about this point right here, and I know I then have bx and by and c, except c passes through it, so then I'd also have a. So causing this point to spin, I'd have my 100 kilonewtons, a, by, and bx, but c wouldn't. But remember the teeter-totter example? It didn't matter what point we picked to sum it about. I'm going to pick this point right here. I'm going to call it dot. I'm going to pick point dot. So I'm going to pick that point right there. Take a look at this. C passes right through it. It doesn't cause it to spin. Look at B. B passes right through it. It doesn't cause it to spin about that point if I put a thumbtack right there. A does, 100 kilonewtons does, and 75 kilonewtons does. But look, I managed to not have to deal with 3 unknowns. I know we've already solved for B, but how easy would it be if I didn't have to worry about the funny one that's going in 2 different directions? So it's often handy to pick a spot that you sum your moments about that kind of eliminates a bunch of your unknowns, or that won't cause it to spin. So I'm going to put my thumbtack right here. I know B passes through the node, so it doesn't cause it to spin. C passes through the node, so it doesn't cause it to spin. A does. A causes it to spin in that direction. If I point my thumb after I've curled my fingers, my thumb points out of the page. So I've got positive A, and it is acting 3 meters away. I've got 100 kilonewtons trying to make it spin in that direction there. I point my thumb into the page, or I point my thumb after curling my fingers in the direction it's trying to spin, and it's negative, so minus 100 times 2 meters. And I've got 75 kilonewtons trying to make it spin in that direction. Curl my fingers in the direction it's trying to spin and point my thumb. It's pointing out of the page, so it is positive 75 times 4 meters. I can rearrange this. I'll bring my minus 100 times 2 over to this side, or 100 times 2. Bring this over and it becomes a negative, minus 75 times 4, and I get minus 100 divided by 3. And I get that A equals minus 33.3 kilonewtons. Well, what does a negative number tell me? A negative number tells me I guessed wrong. So since I always guess things to be in tension, that means a negative will always tell me that it's really in compression. So I have A equals 33.3 kilonewtons in compression. I still have one more unknown. I don't know what the value of C is, so I'm going to sum the forces in the x direction with everything going in that direction being positive. So I've got minus C minus bx. Well, bx is b cosine 56.3, And I know that B is 30, so it's minus 30 times the cosine of 56.31 degrees. So this was just Bx. And I've got minus A. Minus A I've drawn in that direction, but I calculated a negative number. So I've got minus 33.3. I am going to bring C over here and make it positive, and I am left with this right here. I have minus 30 times the cos of 56.31 minus a negative value of 33.3. And I end up with C equals 16.66 kilonewtons. It's a positive number. That means I guessed right, and I guessed that it was in tension. So I still, no matter what way I do it, get A equals 33.3 kilonewtons in compression, B equals 30 kilonewtons in tension, and C equals 16.6 kilonewtons in tension. So it didn't matter if I kept the left side or the right side, I got the exact same values. So now we know it doesn't matter what way we cut it, as long as we include all the forces and reactions that happen on the side we keep. We didn't need to draw the 100 kilonewtons here because it didn't work, it wasn't applied in the section that we kept. But we know that that 25 kilonewtons is directly related to that 100 kilonewtons. So you can see here that we found that this member had 16.7 kilonewtons in tension. This member had 30 kilonewtons in tension, and this member had 33.3 kilonewtons in compression. In this example, I've drawn it going towards the point, which means compression. Well, that's great. We found 3 members out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 members. There are 17 members, and we found the internal forces for 3. You can see why this is a long lecture, because yes, my good friends, we are going to find the rest of the forces. So find the forces in the rest of the members of Truss 1. Here's a thing that I find handy to keep track of things. I and most engineers will label the truss with letters as the members and numbers for the nodes. And that becomes really handy for labeling your unknown internal truss force members and then using the numbers of the nodes to think about what point you're spinning your section about. So let's try labeling this truss. So here we've labeled it A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. So every member has a label, and every node has a number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to go through and find all of the internal forces on this truss, and then we can use these labels and these nodes to help us keep track of what we've done. So let's go through that. Again, I always find it handy to draw these things out. I know we've already drawn this one out. Well, no, let's draw it out again. I find it, let's draw it out again. And we know that this is 3 meters. And we know that all of those bays are 2 meters each. We know that there was an applied load of 100 kilonewtons right here. We've already solved for the reactions, and we know that this is 75 kilonewtons, and we know that this is 25 kilonewtons, and we know that that is 0 kilonewtons. We've labeled this A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. We've also labeled our nodes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, I am always going to find it handy to keep a little chart here so we don't lose track and make sure we haven't forgotten anything. I'm just going to write A, B, C, D, E, F, 1, 2, 3, 4, 5, 6, E, F, G, H, I, J, K, L, M, N, O, P, Q. So that we can fill this in so that we don't lose track, that we don't forget. Remember, one handy thing is we've already done this cut. We already found K, D, and O. We already found them because the way we did it before, we had just labeled them A, B, and C. So we had found that A, which is K here, A was 33.3 kilonewtons in compression. So 33.3 kilonewtons in compression. D was B over here, was 30 kilonewtons in tension. And we found O was 16.666667 kilonewtons in tension. So we've already found 3 of our sections, or 3 of our members. We're now going to want to go through and do a bunch of sections to find all of the points. Now, I'm sure some of you have taken engineering classes in the past, and you guys are sitting there saying, Shannon, you haven't talked about method of joints. Well, here is a mind blower for those people. The rest of you probably don't give a hoot because what the hell, you just learned about method of sections. Why would you possibly know what method of joints is? Method of joints is when we make a cut about a node. But really, it is just method of sections. It's a smaller method of sections. It's just that we're taking a much smaller section. So you could call this lecture method of sections and joints in one lecture section. But really, it's kind of a misnomer that they ever even introduce method of joints. I find it creates this impression that they're two different things, but they're the exact same thing. So we're just going to treat them all as method of sections. Some of them just won't ever have any forces that cause a moment. That's it. So let's start with our very first section, and I am going to make a section cut through A and N. I'm going to draw a section through that line right there. Or I am going to go, so let's do, let's make a section. A section through A and N. So what I'm saying is that I'm keeping this point right here, which we've called 0. I'm cutting through N, and I'm cutting through A. I have 0 kilonewtons here, and 25 kilonewtons here. And these are the two members I'm cutting, that's A and B. But I don't know what those internal forces are, so I'm going to draw them in tension. So this is A and N. I've got A, and I've got my unknown N. So you can see, this is what some people would call method of joints. I've cut that every single force passes through the joint. We don't have anything that causes a moment, but it's kind of irrelevant. Let's sum our forces in the x direction, where everything going in that direction is positive. We've got 0 plus N equals 0. N equals 0. N has no force associated with it. We can sum the forces in the y direction. We have A going upwards, which is our positive direction, and we've got 25 kilonewtons going upwards as a reaction. A equals minus 25 kilonewtons. I guessed A was in tension. I've got a negative number, that means I guessed wrong, or that A equals 25 kilonewtons in compression. Well, I can come fill those in now. A is 25 kilonewtons in compression, and N equals 0. So we've got 2 more members out of our 17. We've got 5 out of our 17 now. Let's make a cut through J, B, and N now. Let's do section J, B, N. I'm going to go get myself a water. I did hills today, which means I am very, very tired, and then I also had too much wine last night, so give me just a minute. All right, let's start making our next cut, which is the Jbn cut. I'm going to draw it a little bit smaller this time, just because I kind of know what we're doing now. Well, I didn't draw that very well, did I? All right. I'm already throwing things off here. Okay. We're going to cut through J, B, and N. So we have J, B, and N. And we know we have 25 kilonewtons here and 0 kilonewtons here. We know that B can be broken up into Bx and By. And we know from previous versions of this, all of these angles relative to the x-axis are the same. We know that By equals B sine 56.31 degrees, and bx equals b cos 56.31 degrees. We can now sum the, let's sum the forces in the y direction. So we can sum the forces in the y direction equals 0. So everything upwards is positive. We've got 25 kilonewtons going upwards, and we've got by going downwards, so negative. So we've got by going down. By is b sine 56.3. And those are the only two things in the y direction. So we can now solve for b. We can take this over to this side, and we end up with 25 divided by the sine of 56.31 degrees, and we get b equals 30 kilonewtons. We guessed that it was in tension. It's a positive number, so it is in fact in tension. We can sum the moments about a point. Sum the moments about the z-axis, where everything in that direction is a positive. We want to know what it takes to be 0. I am going to pick, no, I'm not going to pick that point. Look at this, we've already solved for n here. Look, we've solved for n already. We know that n equals 0. I'm not going to use that equation. We now know b, we now know n. We want to know what j is. J is the only thing we have left that we don't know. I'm going to sum the forces in the x direction, everything going in that direction being positive. We've got j going in the positive direction. We've got n going in the positive direction, but it's 0. We've got 0 going in the positive direction, but it's 0. So we're left with bx going in the positive direction, so plus bx, but we know that bx is b cosine 56.31, and we've already solved for b, so it's 30 cos 56.31 degrees equals 0. We can solve for j. J equals the negative of 30 times cosine of 56.31. Or j equals minus 16.64 kilonewtons. Or j equals 16.64 kilonewtons in compression. All right, so we've got two more things we can fill out in here. We've solved for, well, we solved for b, and we solved for j. So we filled in b, and now we can fill in j. We've got 16.64 kilonewtons in compression. So now we've got 6 elements that we have solved for. So we had already solved for 3. B and J. I already solved for 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. What am I missing? A and N. We had already solved for K, D. Oh, some of you must be so mad at me. When we solved before, we solved B here. That was D here. This is the 30 kilonewtons in tension we just solved for. I should have filled that one in before as D. So K, D, and O, K, D, and O, we had solved for before. I'm even going to flag those. I'm going to say that D was B, and K had been A, and oh my goodness, what is my problem? And O had been C. Now we've solved for B and J. It's just a coincidence that the value is the same. So now we have 7 new values that we've solved for, 7 values total that we've solved for. So now we can make another cut. We've cut through here, here. What if we cut through L, F, and P now? So let's make a cut through L, F, and P. So we know that this is 3 meters, and we know that that's 2 meters, and that's 2 meters. We know that there is a reaction here of 25 kilonewtons, and that is 0. And then we have unknown internal forces here that I am going to draw in the positive direction, or in the tensile direction, not in the positive direction. I'm going to draw them in tension. L, F, and P. I'm going to use the tricks I have available to me to solve for these. F, I know, is in that same angle. That angle is the same where each bay is 2 meters wide and 3 meters tall. So that angle there is 56.3, the same way we've solved it before. So Fy is F times the sine of 56.31 degrees, and Fx is F times the cos of 56.31 degrees. Now we can start summing our forces in different directions. Let's sum our forces in the, well, I'm going to draw out, I find it helpful to draw out Fx and Fy sometimes. Let's sum our forces in the y direction, where everything upwards is positive, and we want to know what it takes for the sum of all the forces in the y direction to be positive, or what the internal forces are that make this true. We have 25 kilonewtons acting upwards, and we have Fy acting upwards. It's the only other thing in the y direction. So it's positive, it's Fy, it's going up. Fy, we know is F sine 56.31. F sine 56.31 degrees. Those are the only things in the y direction. So I can solve for F. I have the 25 over here divided by the sine of 56.31, and I get that F equals minus 30 kilonewtons. Well, I know that anything I draw, I drew everything in tension, so if I get a negative number, that really means that F is 30 kilonewtons in compression. I am going to sum the moments about a point in the z-axis, and everything spinning in that direction is positive. And we had labeled all of our nodes. I am going to pick node 4 to spin about. So I am going to use node 4. Remember when we labeled everything, this node right here we labeled as node 4. So that's node 4 right there. I'm going to pick node 4 to spin everything about. If it passes through the node, it doesn't cause a moment. To have a moment, it has to have a force and a distance from the point we're spinning about. That's what causes a moment. So we have this node right here. P passes through it. F passes through it. So that gets rid of all of those things. The only thing causing this to spin about this point right here is our 25 kilonewtons and our L. 25 kilonewtons is trying to spin about this point right here like that. I point my finger in the direction it's trying to spin. My thumb points down. I have minus 25 kilonewtons. And to be a moment, you need force times distance. We are 4 meters away. P passes through it, F passes through it. L is trying to make it spin in that direction, so I curl my fingers in the direction it's trying to make it spin, point my thumb down. It is also negative, so minus L times, and L is 3 meters away. And those are the only things trying to make it spin about that point. So we can solve for L. We'll bring that over and it's positive. So we have 25 times 4, but divided by negative 3, we have L equals minus 33.3 kilonewtons, or L is 33.3 kilonewtons in compression. So we've solved for F and we've solved for L. Now, let's do our very last one. We have 3 equations available to us. Sum our forces in the x direction with everything going in that direction being positive. Well, we have our 0 kilonewtons. We have L going in that direction. We've calculated, so L is going in the positive direction, but we know it is minus 33.3. We've got Fx going in that direction, which is positive. Fx is F cosine of 56.31, and F was minus 30. And we've got P going in that direction, or plus P equals 0. We can rearrange this and solve for P. P equals, we're going to bring our minus 33.3 over to this side. So we've got 33.3. This is a negative, and we're going to bring it over to that side. And so we're going to add that over. We're going to bring that over, it becomes positive. We'll bring that over, it becomes positive. So plus 30 times cosine of 56.31, and we get P, this is a small rounding error here, P equals 50 kilonewtons. It was positive, so really we're saying we had 33.3333 plus 30 times the cos of 56.31. You can see that that rounds up to 50. We've got 50 kilonewtons positive, which means it was in tension. So we've solved for all three unknowns here. We can come back to our list of unknowns. We solved for F. F was 30 kilonewtons in compression. L is 33.3 kilonewtons in compression. And we solved for P, which is 50 kilonewtons in tension. So we're getting down there. We've solved for most of them now. We made a cut here, here, and here. Let's make a cut here. Let's cut through M, H, and Q. Let's make a cut through M, H, and Q. So let's draw a small version of this. Just redrawing our section that we're cutting. So we're cutting through M, H, and Q here. We know that this is 3 meters tall. And we know that that is 2 meters and 2 meters and 2 meters. We know that is 25 kilonewtons, and that is 0 kilonewtons. But look, we're cutting now where we have 100 kilonewtons on here. We've cut far enough over that we have a spot that 100 kilonewtons is showing up. And then we've cut through M, H, and Q. We don't know what the value is. We don't know if they're in tension or compression. So I'm going to assume they're all in tension. And if I get a negative number, I'll know that I assumed wrong. So let's break this down a little bit. We know H can be HX and HY. We know that the angle is the same to the x-axis as all of them are because they have a ratio of 3 meters to 2 meters. So that means we know that, that HY equals H times the sine of 56.31 degrees, and that HX equals H times the cosine of 56.31 degrees. We're going to sum our forces in the y direction with everything upwards being positive. We have our 25 kilonewtons upwards. We have our 100 kilonewtons downwards. And we have HY upwards. HY is H sine of 56.31 degrees. All equals 0.
Doctor.
What?
I have to go to the doctor.
Oh, right, you have a doctor's appointment. That's right. He showed me his health card as if that told me exactly what he was doing, and I was very, very confused. But apparently health card means doctor's appointment. We spend a lot of time together lately. But we never actually get to talk to each other. So we now have one unknown, one equation. We can solve for H. H equals, we'll bring everything over, 100 minus 25 divided by the sine of 56.31 degrees. And we get, just want to make sure I haven't done anything silly and giving you guys funny numbers. Where are we cutting through now? Next page. Excellent. H is 90.1 kilonewtons. It's a positive number. We drew it in tension, so that means we were right. It is actually in tension. Let's sum the moments about the z-axis, where everything in that direction is 0, or everything in that direction is positive, and let's pick this node right here. Let's go back and look at our master diagram. That node is 6, so we're going to spin this about node 6. So we're going to imagine we're spinning it about node 6. Well, if that's node 6, Q passes through it, H passes through it, the 100 kilonewtons passes through it. If I have a thumbtack there, the only things trying to make it spin are the 25 kilonewtons and M. So if I've got a thumbtack right here, 25 kilonewtons is trying to spin it in that direction. I put my thumb down, it's trying to spin it in the negative direction. I've got minus 25 times 246 meters. M is also trying to spin it in the negative direction, so I've got minus M, and M is 3 meters away. Those are the only two things trying to make this spin about node 6. If we picked a different node, it would be a different story, but we've picked node 6. We have one unknown, one equation. We can rearrange this. We bring this over here, and we've got 25 times 6 divided by -3, and we get M equals minus 50 kilonewtons. I assumed that this was in tension. That means that my negative number tells me I was wrong, and that M equals 50 kilonewtons in compression. I'm going to sum all the forces in the x direction. So everything in that direction is 0, or everything in that direction is positive. I've got 0 kilonewtons. I've got M, which is in the drawn in the positive direction, so plus M, but M is minus 50. I've got HX, which is positive, so plus HX. HX is H times the cosine of 56.31, and H is 90.1. And I've got Q, or plus Q, equals 0, because Q is also drawn in the positive direction. I can rearrange this, and I can solve for Q. I'll bring my 50 kilonewtons over, and it becomes positive. I bring that over, and it's minus 90.1 times the cos of 56.31, and I end up with Q equals 0. Q equals 0. So I have 3 more things I can fill in on my master chart here. I've solved for H, and H is 90.1 kilonewtons in tension. So H is 90.1 kilonewtons in tension. I solved for M, which was 50 kilonewtons in compression. And I've solved for Q, which is 0. So we still have C, E, G, and I left to solve for. So I wonder if doing some smaller cuts would be handy for us here. I am going to start with a cut through N, B, C, and O. So I'm going to do a cut through here. Or I'm going to call it section N, B, C, and O. So I'm going to make a cut through or around essentially node 2. So this is node 2. I probably drew that a little bit too big. I'm going to draw all of these as if they were in tension. And this was N, B, C, and O. Now, here's the handy thing. We've already solved for some of these. Some of these have already been solved for. Let's take a look. Let's see what ones we know. Well, we know that N equals 0. B equals 30, and it is actually in tension, so B equals 30. C hasn't been solved for, and O has also been solved for. 16.67 kilonewtons in tension, so O equals 16.67 kilonewtons. So it looks like C is our only unknown here. B, we know, can be broken into By and Bx. We now have gotten used to this whole, if it's the y, it's the sine of the angle. If it's the x of the force, it's the cosine of the angle. I am going to sum my forces in the y direction with everything upwards being positive. I've got C going upwards, and I've got By going upwards, so plus By. By, we know, is B times the sine of 56.31, or 30 times the sine of 56.31. This is really By equals B sine 56.31. But we want to start getting fast at this. We don't want to have to keep writing all of these steps out. So I'm starting to make it quicker and quicker as we do it. But that's just there for you as a reference. So those are the only two things pointing upwards. So we can rearrange this, and we find that C, we're going to bring this over here so it becomes negative 30 times the sine of 56.31. And we get C equals minus 25 kilonewtons. A negative means we have drawn our arrow wrong. I assumed it was in tension. So that means C is 25 kilonewtons in compression. The only thing we didn't know in that was C, which we solved for. 25 kilonewtons in compression. Let's make another cut. Let's maybe make a cut. Let's make the cut through K, E, and L. That'll give us E that we can try to solve through. So let's make section K, E, and L. We know that that is node 5, and we're going to draw them all in tension. K, E, and L. We've already solved for some of these. We know that K is 33 kilonewtons in compression. I've drawn it in tension, so that means K is minus 33.3. And L is 33 kilonewtons in compression. I've drawn it in tension, so it equals minus 33.3. E, we don't know. Let's sum our forces in the y direction, where everything upwards is positive. We've got minus E. There's nothing else in the y direction. E equals 0 kilonewtons. So E equals 0 kilonewtons. We still have two unknowns, G and I. Let's make a cut through P, G, H, and Q. So P, G, H, and Q. This is node 6. We have P, G, H, and Q. We know some of these already, so let's fill in the ones we know. Well, we know P is 50 kilonewtons in tension. And we've drawn it in tension, so that works out nice. Q equals 0. H equals 90.1 kilonewtons in tension, or 90.1 kilonewtons. H can be broken up into Hx and Hy, and we know that Hy is H times the sine of 56.31, and Hx equals H times the cosine of 56.31. Let's sum our forces in the y direction, where everything upwards is positive. We've got G, and the only other thing going upwards is Hy, so plus Hy, and we know Hy is H times the sine of 56.31, and H is 90.1. And that equals 0. And just for those of you that want the refresher, that was just Hy equals H times the sine 56.31. We can solve for G. We bring this over. We've got minus 90 times the sine of 56.31. Something is funny with my calculator, because this should be rounding. This normally rounds nice and even to 75. Oh, I know what it is. I only put 90. I was like, something seems funny. So negative 90.1 times the sine of 56.31, and that's pretty darn close. If we round that up, we've got G equals 75 kilonewtons, but it's minus. So G equals 75 kilonewtons in compression. So we can fill this in. 75 kilonewtons in compression. The last one we need to know is I. Let's make a cut through Q and I. I need a new page for one tiny little cut. Oh, that's nice. We can come back and do our axial force diagram on it. All right. We want to make the cut. We want to make section cut QI. So we're cutting through Q and I. This is node 8. We've got our I and our Q both drawn in the tensile direction. We know that at node 8 there is also a 75 kilonewton reaction happening there. We have already solved previously for Q. We know that Q equals 0. Let's sum the forces in the y direction, where everything upwards is positive. We've got positive I plus 75 equals 0. I equals minus 75 kilonewtons, or I equals 75 kilonewtons in compression. We can come over here and fill that into our chart. 75 kilonewtons in compression. So now we know all of the internal forces in this truss to get 100 kilonewtons out to the reactions, or out to the supports. That means not only do we need to design something here to take these loads, every internal member needs to be strong enough to resist at least this load. So for example, member I needs to be able to resist 75 kilonewtons in compression. Member H needs to be able to resist 90.1 kilonewtons in tension. And remember, the whole point that we're trying to do is to make sure that the capacity, or the reduced capacity, is greater than the factored load. We have figured out the loads in every member of this particular truss. I know, it's a slog of a calculation, but as you do it, you start to get faster at it. I have definitely given you hard ones in the assignment. There are a few questions that are in there for some of the easier ones that, trust me, the questions where you have to answer with math aren't that difficult. You might make them difficult, but those are the easy ones. You can stop and think about it, and some of it you can do without even putting pen to paper. You should try doing it. Write down your answer, and then maybe do a little bit of math and try to verify out your answer. The really hard ones, I have given you, I want you to try them. You don't have to show your work for those ones, but you should try them, and then I will provide you the answer solutions next week so that you can practice, you can try. For those people that really like to practice to learn things, you'll have them, but it won't be based on points, and then you'll get full answer sheets next week for it. So look at this. Here is our truss solved, written out with all the forces on it. So this is great. I like this. But what would be handy would be to have a little diagram that maybe illustrated this for us in a very handy way. I'm just going to even zip through, and I'm going to introduce this concept right now. We'll come back and do a few more examples, but I want to introduce axial force diagrams. It is a graphical illustration of the axial force at any given point on a member. So if we made a cut right through here and we went through the process of summing the forces in the y direction, we would find that this member has 20 kilonewtons of compression in it. So we could even do that. Let's hope my computer doesn't freeze on me. Let's call that A. We're making a cut. We're making a cut through there. we see that A equals 200 kilonewtons in compression. I think intuitively you probably could have figured that out with this one, that you intuitively know that there's a reaction here pushing up and that this column is being squashed. Well, what we will often do is use a handy little diagram to illustrate that for us. What happens if we have this diagram? We would cut right here, and we could do the same thing and find that from here to here, there's 200 kilonewtons of compression. If we did a section here, we would find that we had 200 kilonewtons down and 300 kilonewtons down, and so that from here to here, we have 500 kilonewtons of compression. Note that it's not 300, it is the 200 from here and the 300 from here. Or 200 kilonewtons from here to here, and 500 kilonewtons from here to here. These are axial force diagrams, and we really like them because it helps us at a glance to see what the crap is going on. Because as we saw with that truss, that was a heck of a lot of data points that wasn't really that helpful to us. So let's take a look at that truss that we had just done, and I'll use that third page to draw it out for us. So here's me, yes, once again, redrawing this truss. If you're annoyed with watching me draw it, imagine how I feel drawing it again. Okay. Well, that was annoying. Let's do it once again. One more time for the win, people. By the way, I would expect your notes to be very, very neat because you would have time to go back and redo it if you're presenting your project or if you're submitting your project. I would hope you wouldn't scribble on it like this. You can do a rough copy and be more than happy to scribble on it as much as you like, but then maybe you would erase that if you were presenting your final copy for me to review. So we have our list that shows us what all the forces are and what all the labels are for everything. And let's go through and draw an axial force diagram. So the top chord is along here, and we have J, K, L, and M. So J is 16.64, K is 33.3, L is 33.3 in compression, and M is 50 kilonewtons in compression. So we have, let's say that's 50, and then we dropped down to 33.3, and then we dropped down to 16.67. This is compression. And so this was 16.7, this was 33.3, and that was 50. Let's take a look at our bottom chord. Our bottom chord was NOPQ. Well, N was 0, O was 16.67 in tension, P was 50 in tension, and Q was 0. So P was 50, and we drop down right to 0, and we drop down to 16.7, and then down to 0. So this is tension. I recommend either using different colors for tension or compression or different hatchings for tension or compression, but tension and compression aren't the same thing. Illustrating that they're different in this is very important It's hard for you to see on my paper, it's very clear, but the recording makes purple and blue look the same. I apologize for that, but you can see I've hatched them differently. We have this member here as A, and it had 25 kilonewtons of compression in it. And I draw ones hatched that way as compression. B had 30 kilonewtons of tension, and my blue is tension. And I'm hatching that way. C had 25 kilonewtons of compression. D had 30 kilonewtons of tension. E had 0. F had 30 kilonewtons of compression. G, which is right here, has 75 kilonewtons of compression. That's a lot. Member H has 90.1 kilonewtons of tension. And then our very last member, I, had 75 kilonewtons of compression in it. Now, I know it looks messy right here. Sometimes what we'll do is maybe do two separate diagrams where one is the top chords and then one is the webs. But what's nice about this, and I didn't draw it completely to scale with the webs here, but it's really nice that you can see, okay, at a glance, here's where the worst compression is in my top chord, and here's where my worst tension is in my bottom chord. Engineers really like these. I have projects, and actually lots of projects we do, where we will actually provide these diagrams for the fabricator. It allows them to know kind of where they can make splices and connections between things. There's a lot of embedded information in that diagram. So here that is. I've made it a little bit easier where I've just drawn the top and bottom chords, but you would typically draw the chords as well, but it just made the example a little bit hard to read. I'm going to go back and change the color of these just so that you have something that's easy to see at a glance. Let's go back and do the next example. All right, here is our newest truss. This truss has reactions here and applied loads of 60 kilonewtons at the bottom chord of each element. Okay, like I said, this is, if you find it easy, you don't have to follow along and watch this example. If you would prefer to practice it and try it on your own, the solutions are provided. But I'm going to go through and talk through it for you because some people like to hear the verbal explanation. Again, this is not mandatory that you watch all the examples, although I would suggest everybody watch the next example, which is our braced frame example. So let's go through and do truss 2. We have 6 bays of 10 meters, and it's 8 meters tall, and we've got 60 kilonewtons applied at each bottom chord node. So the very first thing we do is, well, we're going to get in the habit, again, of drawing our truss. So we have 1, 2, 3, 4, 5, 6 bays of 10 meters. And this is 8. So we always like to write our dimensions on these things. This is 6 at 10 meters. And this is 8 meters. And we know that we have our left side and our right side. We don't know what our reactions are, but we do know that we have applied loads of 60 kilonewtons, 60 kilonewtons, 60 kilonewtons, 60 kilonewtons, and 60 kilonewtons. We can sum our forces in the x direction, where everything going in that direction is positive, and we get that Rx equals 0. We can sum the moments about the z-axis, where everything in that direction is positive, and I'm going to pick that point right there. Let's call it point O, or 0. So I'm going to spin it about that point right there. I have 60 kilonewtons trying to spin it in that direction, or the negative direction, and I have that a few times getting farther and farther and farther away. So I have minus 60 times 10, minus 60 times 20, minus 60 times 30, minus 60 times 40, 10, 20, 30, 40, minus 60 times 50. And then I have my reaction in the right, on the right side, trying to spin it in that direction, or positive, plus our R times 60 equals 0. I can now rearrange all this, and I can find that RR equals, these will all come over and be positive. I've got 60 times 10 plus 60 times 20 plus 60 times 30 plus 60 times 40 plus 60 times 50 divided by 60. I get RR equals 150 kilonewtons. I can sum my forces in the y direction, where upwards is positive. I've got RL plus RR, which I know is 150, minus 60 times 1, 2, 3, 4, 5 times. I have 5 of them. $60 times 5, that comes over and becomes positive, minus 150. RL equals 150 kilonewtons. You probably looked at this and guessed that these would share the loads equally. This is an evenly loaded truss. Intuitively, you understand that these two should be equal just by glancing at these loads. It's one of those things that intuitively you understand. Well, let's talk about two things. We know that we're going to want to go through and label this and solve for all the forces. What do you think we could do to make this half the work we might normally do? Anything that you can think of about this truss? Well, to me, it looks the exact same about this point right here. It looks like a mirror image of itself. That if I found what this force was, it would be the same as that force. Whatever the force in this one is, it would be the same in that. So maybe I only have to solve for half of the members, knowing it's a mirror image of itself. One thing I want to point out is the fact that the forces are applied to the bottom chord is important. If they were applied to the top chord, you could imagine that things would want to be in compression. If you apply them to the bottom, some of these elements would be in tension instead. So in your project, you are going to have a truss that is a roof truss, and those typically get loaded at the top. So similar to our last example, the point loads would come in to the top chord of the element. This example is more like, I don't know, a train bridge, a trestle bridge, where the loads would be applied to the bottom. So don't just assume because I've done an example where there are loads at the bottom that that is where the loads are in your project. Your project is going to have the loads coming in at the top. So we've decided that it's a mirror image, so we only need to solve for everything on this side. Let's label this. Let's call this A, B, C, D, E, F, and G, H, I, and J, K, L, and M. We'll call this node 0, 1, 2, 3, 4, 5, 6, and 7. The other thing that might be handy to do right now is to figure out what this angle is. Because we know if we know that angle, these are all the same as each other. Now, if you guys are going to do an assignment question where it's not the same angle, you will need to figure out multiple angles. Again, that is for you to practice with. Go as far as you think is helpful for you. I know some people like lots of examples. I can guarantee you that those examples are harder than anything you will do in the exam. I know some people very much would prefer to do something 10 times harder to practice with so that the exam seems very easy. And that is what I have given you with the assignment for trusses. So let's figure out what this angle is. We know that we have 10-meter bays that are 8 meters tall, and this is the angle that we want to solve for. We have opposite over adjacent, which is tangent of the angle equals opposite over adjacent, or our angle equals the inverse tangent of 8 divided by 10. Or we get an angle of 38.66 degrees. So that means now going forward, whatever, whether we're talking about B, D, or F, the y component will be the force. The y component of it will be the hypotenuse times the sine of the angle, and the x component will be the hypotenuse times the cosine of the angle, because we like to develop routines. Let's go through and start making our cuts. Let's maybe start with I'm going to go through and kind of be systematic here. Let's cut through H, B, and K. Actually, do you know what I'm going to do? I'm not going to make my section cut right now. I'm going to label these out so that I don't miss anything. This is exactly what I did last time. A, B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So A, B, C, D, E, F, G, H, I, J, K, L, M. And we want to come back and fill all of these in. Let's do section H, B, K. So you can pick however you want. You can pick doing it from the left or the right. I am lazy, like I said, I like to have systems. I'm going to always just keep cutting from this direction and keeping my left-hand side. You will see that the way I have posted in the lecture slides, I switch it back and forth just to show you that it doesn't matter. So I'm going to go through and do all of them this way. I just realized I am going to have to, this lecture is so long to film that my nanny is going to leave, and I hope my husband comes back from his doctor's appointment so he can relieve the nanny. Okay, so let's draw this cutting through H, B, and K. We have a reaction here that we've solved for of 150 kilonewtons. And we have unknown internal forces H, B, and K. We know that B can be broken into By and Bx. But we also now know that, that for whatever the force is, the y component is using the sine of the angle, and the x component is using the cosine of the angle. So we can go through and start thinking about summing these up. That's 0. And that's 8 meters. So let's sum our forces in the y direction. We have 150 kilonewtons going upwards, and we have By going upwards, or plus By, and we know By is B times the sine of our angle, which is 38.66 degrees. That is the only, those are the only elements going upwards. So we can rearrange this and we can solve for B. We bring this over, it becomes negative, so minus 150 divided by the sine of 38.66, and we get minus 240.1. That was weird. That was my husband's computer. I have no idea what that noise was. So B equals 240.1 kilonewtons in compression. So we can fill in our first thing here, 240.1 kilonewtons in compression. Let's sum our moments about a point. Let's pick this point right here. Let's pick point 0. Let's sum our moments about the z-axis, where everything's spinning in that direction is 0, about point 0. 150 kilonewtons passes through it, K passes through it, B passes through it. We have H trying to spin it in that direction, which is negative, so minus H times 8 meters, that's the only thing trying to spin it, equals 0, H equals 0 kilonewtons. So H equals 0 kilonewtons. We can sum our, forces in the x direction, where everything going in that way is positive. We have H, which is 0, Bx, we have K, and then we have Bx, so plus Bx, And we know Bx is B times the cosine of 38.68, and we've solved for B. B is minus 240.1. So remember, this is our Bx, this is all just Bx. We can rearrange this, and K equals 240.1 times the cosine of 38.66, or 187.5. K equals 187.5 kilonewtons. It's positive. I guessed it was positive, or I guessed it was in tension. A positive means I'm right, so that's in tension. So K equals 187.5 kilonewtons in tension. Let's do our next cut. Let's cut through I, D, and L. Section I, D, and L. We know that that is 8 meters, and we know that that is 10 meters. We have a reaction here of 150 kilonewtons. We also, at this node here, have an applied load of 60 kilonewtons. And then we have our unknown internal loads, I, D, and L. But I'm drawing all in tension because I don't know what they are. I am going to sum my forces in the y direction, where everything upwards is positive. That's dx, and that's dy. We have dy going upwards, so positive dy. Now dy, we know, is d times the sine of 38.66. So plus d times the sine of 38.66. We've got 150 kilonewtons going upwards, and we've got 60 kilonewtons going downwards. Those are the only things acting in the y direction. We can solve for d. We can bring our 150 over and it becomes negative. We can bring our 60 over and it becomes positive. So we have negative 150 plus 60 divided by the sine of 38.66, and we get that d equals minus 144.07 kilonewtons. We know that a negative means that we guessed wrong. I always guess that they're in tension. So that means D equals 144.07 kilonewtons in compression. D equals 144.07 kilonewtons in compression. We can sum the moments about the z-axis, where everything spinning in that direction is 0, and I am going to pick this node here, which is 0, 1, 2. I'm going to pick node 2 to spin this about. What I like about that is I don't have to deal with dx and dy. L goes right through it, and a 60 happens to go right through it. I end up with 150 and I both trying to spin this about node 2. I tries to spin it in this direction. If I use my right hand, that means it's negative. So I've got minus I times, so to be a moment, you need a force and an eccentricity. I passes 8 meters away from point 2. And I've got 150 kilonewtons trying to spin it in that direction, which is the negative direction. I've got minus 150. And 150 passes 10 meters away from point 2. Those are the only things trying to make this spin about node 2. I equals, I bring this over here and it becomes positive, but then I divide by a negative 8. I've got 150 times 10 divided by negative 8. I get I equals minus 187.5 kilonewtons. It's negative, which means I guessed wrong, and I always guess tension. So I equals 187.5 kilonewtons in compression. So I equals 187.5 kilonewtons in compression. And I can sum the forces in the x direction, where everything in that direction is positive. I've got I going in the positive direction, but it's actually in compression. I've got L going in the positive direction. I don't know what the value of L is. And I've got plus dx. Well, dx is d times the cosine of 38.66. D is minus 144.07. And so then times the cosine of 38.66 degrees. So now we can solve for L. L equals, we're going to bring this negative number over and make it positive, and we'll bring that negative number over and make it positive. We get 187.5 plus 144.07 times the cos of 38.66, and we get 300. L equals 300 kilonewtons. I have a positive number. That means I guessed correctly. I guessed it was in tension. So L equals 300 kilonewtons in tension. So we've got 6 of our 13 forces now. We're starting to get there. We're going to have to do a few more sections. So we've cut through HBK, we've cut through IDL. Let's cut through JFM now. We'll cut through JFM now. So I'll draw this section for myself just to help me keep track of things. We know that this is 10 meters and 10 meters. This is 8 meters. We know there's 150 kilonewtons here as a reaction. And we know that there is 60 kilonewtons here and 60 kilonewtons here. We can draw these in, but they're not really doing anything for us at the moment. Like, we're not solving for those anyway. we have our unknown internal forces, J, F, and M. I don't know what direction they're in, so I don't know if they're tension or compression. So I'm going to draw them in tension because I don't know. And now I'm going to go through the same exercise. I am going to sum the forces in the y directions, assuming everything upwards is positive. Upwards, I have Fy and Fx. Sorry, I have Fy going upwards. So I have positive Fy. We know that Fy is F times the sine of 38.66. So plus F times the sine of 38.66. We have plus 150 minus 60 minus 60. We can solve for F. F equals, we'll bring this over and it becomes positive, or it becomes negative. These come over and become positive. So we have minus 150 plus 60 plus 60 divided by the sine of 38.66. And we get that F equals minus 48 kilonewtons. Just want to check and make sure that that matches up with everything else. Yep, minus 48.0 kilonewtons, or F equals 48.0 kilonewtons in compression. We can fill that into our chart. F equals 48.0 kilonewtons in compression. We can sum the moments about a point, about the z-axis. Maybe you're finding it noticeable, but I like to pick that point right there if it means I can get rid of the annoying f, y, and fx components, because f passes right through that node. This is node 4, so I'm spinning it about node 4. I'm putting a thumbtack right there and trying to spin this about that point. M passes through the node, F passes through the node, and this 60 kilonewtons passes through the node. I have 150 trying to spin it that way, 60 trying to spin it that way, and J trying to spin it that way. J is negative, so minus J, and J passes 8 meters away. I've got 150 spinning it in that direction, which is positive. Wait, no. J is negative, or 150 is negative, minus 150. So the 150 is trying to spin it in that direction. If I curl my finger in that direction, my thumb points into the page. So it's minus 150 times 20. And then 60 kilonewtons is trying to spin it that way. Or curling my fingers like this, my thumb comes up out of the page, which is plus 60 times 10. We can rearrange this and solve for J. We'll bring this over and it becomes positive. That will be negative, and then we'll divide by negative 8. So we have 150 times 20 minus 60 times 10 divided by negative 8. We get that J equals minus 300. It's a negative number. That means I assumed wrong. I always assume everything is in tension. So that means J is 300 kilonewtons in compression. Now we can sum the forces in the x direction. We have J going in the positive direction, so plus J, but we've calculated that J is negative. We have Fx in the positive direction, so plus Fx. But we know that Fx is F times the cosine of 38.66, and our F is minus 48 times the cosine of 38.66, and we've got plus m. We can rearrange this and solve for m. We bring 300 over, and it's positive, and we bring that over, and it's positive, so plus 48 times the cosine of 38.66, and we get that m equals 337.5 kilonewtons. It's a positive number, which means I assumed correctly, and I always assume tension, so that means it is 337.5 in tension. So we solved for J, which was 300 kilonewtons in compression, and we solved for M, which is 337.5 kilonewtons in tension. So we only have 4 more sections, or 4 more elements to solve for. We've got A, C, E, and G. These ones tend to be easy by doing the smaller sections. In fact, I'm going to do A by cutting through AH. I'm going to solve for AH. I've got this node right here. I have H and A. H we've already solved for. H we solved for and found out H was 0. We can sum our forces in the y direction. Minus A equals 0, or A equals 0 kilonewtons. We can now make a section through here. How about we go through K, C, D, and L? So section K, C, D, and L. So going through that node there. K, C, D, and L. Some of these we already know the value for. We can come and look at our chart. K we've solved for. We know K equals 187.5. D equals minus 144.07 kilonewtons, because I've drawn it in tension, but it's actually in compression, so I'll make it a negative. And L equals 300 kilonewtons. 300 kilonewtons, and it's in tension, so that's correct. We know D has its dx and its dy component. We can sum the forces in the y direction, where everything upwards is positive, and we have C going upwards plus dy, because dy is going upwards, but we know that dy is d times the sine of 38.6. D is minus 144.07 times the sine of 38.66 degrees equals 0. We can rearrange this, and we get that C equals 144.07 times the sine of 38.66. And we get that C equals 90 kilonewtons. It's positive, that means I've guessed right, and I always guess that everything's in tension. So C is 90 kilonewtons in tension. There's no way I'm going to be done this by 4:30. Can you relieve Jackie at 4:30? And Duncan needs to be picked up. Remember, Duncan's not here, so is that okay?
Yeah, for sure. So I relieve Jackie and I'll throw him off in the car and take him.
If he wants, yeah, okay. Thank you. So now we have the value for C. We can fill in C is 90 kilonewtons. We have E and G still to go. So let's make the cut for E. Let's do the same thing. We'll cut through L, E, F, and M. F, E, F, and M. So this is F, E, so this is L, E, F, and M. So this is L, E, F, and M. Have you guys noticed that what I'm looking for is this one here? And so what I really want is F, Y here. I'm just going to go ahead and only fill in Fy, or F. F, we found earlier, is 48 kilonewtons in compression. So it's minus 48 because I've drawn it in tension. We're going to sum our forces in the Y direction, where everything upwards is positive. And we've got E plus Fy, and we know that Fy is F times the sine of 38.6, and our F is minus 48. So times the sine of 38.66 degrees equals 0. We can rearrange this and we can find what E equals. We'll bring this over and it becomes positive. 48 times the sine of 38.66, and we get that E equals 30 kilonewtons. It's a positive number, which means that I assumed correctly. I always assume everything is, I always assume, I did two things wrong. Do you guys know what I did? I was silly, and this is why it's important to sometimes go through things twice. We're summing everything in the Y direction. What did I forget from these sections? $60 kilonewtons and 60 kilonewtons. So this, that's not right. C plus minus 144.07 times the sine of 38.66 minus 60 kilonewtons equals 0. Now we can find what C equals. We bring that over and it's positive, and we bring that over and it's positive. So we have 144.07 times the sine of 38.66 plus 60, and we get C equals 150 kilonewtons. 150 kilonewtons. E, we need to add our minus 60 kilonewtons equals 0. So 48 times the sine of 38.66 plus 60 equals 90. E equals 90 kilonewtons. It's positive, which means I guessed correctly, and I always guess everything is in tension. So now I can fill in that E equals 90 kilonewtons. One section left for this one. Then we have one more example. I know this is a killer lecture, but it gets easier after this. The next lecture, you're actually going to get some answers, and it's actually quicker to do. All right, so now we're going to cut through G. So we're going to go through M, G. We might as well call this M prime if you want to. So section M, G, and M prime. We have M and M prime and G, and I am not going to this time forget my 60 kilonewtons. Well, we know we're just worried about G. I'm not even going to look up M and M prime. Sum of the forces in the y direction equals 0, with an upwards force being positive. G is up, minus 60 kilonewtons equals 0. G equals 60 kilonewtons in tension. This is a mirrored truss. So everything we just did to solve this, we can flip over. And so we will have all of the forces on the entire truss. Let's take a look at this. Here it is all just worked out again. Look at this. 0 and 0 and 0 and 0. If we made those go away, does this start to look like a familiar truss? We've got a truss shaped like this with the load coming in on the bottom chord. Remember, if this was a building, normally we'd be loading up the top. But this is got load coming in on the bottom chord with 0 force in those kind of corner members. Take a look at this. This is a truss you're probably all used to seeing. There's our top chord in blue, our bottom chord in green, and then our web members that could be in tension or compression. If our thing is bending like this, the bottom chord is usually in tension and the top chord is usually in compression, and these web members are interchanging. Let's take a look. All of these bottom chord members were in tension, all of these top chord members were in compression, and these web elements varied. So that's a pretty standard way to look at trusses. So here that is all worked out. Now I know that seemed like a ton of stuff, but look at this. This one example was only 2 pages of calculations. And a lot of that was taken up by pretty drawings. As you can see, keeping track of everything is super important. I made a mistake, and it gave me wrong answers, so that's why it's good to go back and double check what you're drawing. I like using colors to help me keep track of it, but you don't have to. We're going to do one more example, but this one's quick. There's only 4 members that we need to solve for. This is a braced frame. So if this was in a building, it would be in the wall of your building. We have 2 columns and our brace element and a beam that would be at the floor above. Now, in reality, this beam is probably also loaded with load, but we're going to ignore that for now. We're just going to talk about the braced frame being part of the lateral load resisting system. We have 250 kilonewtons of lateral load on this system. We have 2 pins. It's not like at the top where we could assume that was some splaying happening between our elements. We have a pin condition at the bottom of both of these. One of them is not a roller. We don't know how these loads are going to be shared out, so we're going to have to leave some stuff for a minute. We're going to go through this, and I'm going to show you why. So let's go through what we've done on our other examples so far. We're going to start out drawing out our element like we always do. We have our braised frame that is 5 meters tall, an 8-meter bay. We've got a load of 250 kilonewtons applied to it. We have our brace element right here. And we have 2 pinned reactions. We'll call this left X and left Y, and we'll call this right X, and we'll call this right Y. We know step 1 is solving for, oh, look at that off the page. We know step 1 is solving for our reactions. So let's go through and solve for our reactions. We can sum the forces in the X direction. We have Lx going in the positive direction, our X going in the positive direction, and we have minus 250 kilonewtons equals 0. Doesn't seem like there's much else we can do there. Let's now sum our forces in the Y direction, where everything going upwards is positive. We have Ly plus Ry equals 0, or Ly equals minus Ry. So those are going to be equal and opposite to each other, but we have no idea what the value is. And these are not 2 equations and 2 unknowns, because that's the X component and that's the Y component. So we technically have 4 unknowns here. Let's try one more thing. We have summing our moments about the z-axis, with everything going in that direction being positive, and let's pick our left-hand side to sum about. Well, Ly passes through it, Lx passes through it, and Rx passes through it. So all of those pass through our point L. So only Ry and our 250 kilonewtons of applied load try to make it spin. Ry, if we put a thumbtack here, tries to make the page spin like that. If I curl my fingers, that looks like my thumb comes out of the page. So we've got positive Ry times 8 meters, and we've got 250 kilonewtons trying to make it spin in that direction. So positive 250 times, and it comes along this line, the closest it gets is 5 meters, and that equals 0. We can solve for Ry, and Ry equals negative 250 times 5 divided by 8. Ry equals minus 156.25 kilonewtons. Well, look, I drew my arrow pointing upwards. That means my arrow was wrong. I really have a tension force here, something trying to hold this back part of the truss down. You can imagine we've got a load like this, it's trying to make it spin. It wants to lift up out of the ground here. So we need this reaction to make sure it doesn't. Well, now we can go back to this right here. Ly equals the negative of Ry. Ry was a negative number. That looks like Ly equals 156.25 kilonewtons. Well, that's fantastic. We solved these two, but we still don't know how to solve Lx plus Rx. So something seems a little bit kooky there. Let's go through and label our nodes here. Let's label them A, B, C, and D, and we'll label our nodes 0, 1, 2, and 3. So I guess we technically spun that about 0.0. Let's start going through doing our method of sections. I'm going to do a section through AD. So section AD, I only have A and D. This is node 2. I've got my applied load of 250 kilonewtons. And I've got unknown internal loads that I'm going to draw in tension of A and D. It's 428, sorry. Let's sum our forces in the x direction. Everything going in that direction is 0. So we have minus A minus 250 equals 0. We can bring A over. A equals minus 250 kilonewtons. A negative means I assumed wrong, and I always assume everything's in tension. That means A is 250 kilonewtons in compression. Let's sum our forces in the y direction. We have minus D equals 0, or D equals 0. Well, that one was kind of handy. So we've solved for A and we've solved for D. We know that A equals 250 kilonewtons in compression, and we know that D equals 0. Okay, so maybe we're starting to get somewhere now. Let's now maybe cut through B and D. Let's do section B and D. Before we go and do that, let's take a look at what our angle for B is from the ground. That was 5 meters, and that was 8 meters. We can find our angle. That's opposite, that's adjacent. We know that the angle equals the inverse tangent of opposite divided by adjacent, or our angle equals the inverse tangent 5 divided by 8, or 32 degrees. We'll draw through section BD, so we've got this node here, we've got D, we've got B, and we have RY. I'm going to draw RY up, but we know that RY is minus 156.25 kilonewtons. We have D, which we've already solved, is 0, and we have B, which can be broken up into BY and Bx. So we can now sum our forces in the y direction. Let's sum our forces in the y direction. sum our forces in the y direction. We have D equals 0. We have BY going upwards, so positive BY, and BY is B times the sine of our angle, which is 32 degrees. We have our reaction going upwards, so it's positive, but we know its value is minus 156.25 kilonewtons. And then D was 0. So all of that equals 0. We can solve for B now. We solve for B, we bring this over, and it's 156.25 divided by the sine of 32. And we get B equals 295 kilonewtons. It's a positive number, and I always assume that everything is in tension, and a positive number means I assumed right. That means B is 295 kilonewtons in tension. But look at this. There was another thing here. There was a thing I didn't draw here. We had our unknown Rx here at this point. Most of the time, we've been dealing with all of our Rx's being 0. But this node has our Rx here. Let's now sum our forces in the x direction, where everything going in this direction is positive. We've got Bx, which is negative because it's going in that direction, and Bx is B times the cos of 32 degrees, and we've got our Rx, which is going in the positive direction. So Rx equals, let's bring that over, and it's 295 times the cos of 32, or Rx equals 250 kilonewtons. Well, look, we can come back up here to our original equation here. Lx equals 250, Lx plus 250 minus 250 equals 0. Lx equals 0. So we can fill these in. We should have done it already. This equals minus 156.25, and that equals 156.25. Well, now we can put in that that equals 0, and that this equals 250 kilonewtons. Kind of makes sense that this one should be 0, because how could any load get to it? There was nothing to apply the load there. So the only thing left to solve for now is C. Now, I could pick a complicated section and cut through A, B, and C, but I'm lazy. I'm going to cut through section C. Where that's my node, I've got an applied upward load of 156.25, because that's my reaction. That's 0. And that is my unknown value C. I am going to sum my forces in the y direction, where everything upwards is positive. I've got C going upwards, and I've got plus 156.25 kilonewtons. That means C must equal minus 156.25 kilonewtons, which means C is 156.25 kilonewtons in compression. So C equals 156.25 kilonewtons in compression. So it did not take long to solve for this braised frame. Let's go through and look. So here those values are written out. You can see that in this I've drawn the arrow downward and got rid of the negative, because that is the same thing. Here they are worked out. This we've already talked about, so we've talked about that earlier. I jumped through that earlier. Let's take a look at this axial force diagram. This is really handy. This shows us that we have no force in this, and we can quickly see that this is compression and tension. Here is our train bridge, where I've only showed the top and bottom chord, but we would often show the web elements as well. So I know that that was a lot. It really was. There's no other way to go about it. This one is one big, painful lecture, and it always is, and students always hate me for this lecture. You'll start to like me next term, I hope. It gets a little bit better. Next term is the fun term. You finally start to get some answers. But we have to get through this hard stuff. And unfortunately, the hard stuff always comes at the end of a term. That's just the way we can work it. So you should know the free body diagram symbols. You should know how to solve for reactions. You should know method of sections. If the whole is in equilibrium, then part of it is in equilibrium. How to use method of sections for truss analysis. You should understand where the top chord, bottom chord, and web elements on something is. You should know how to draw an axial force diagram for trusses, columns, and brace frames. You are going to have to draw that in your project part 2. I will want to see a column diagram and your truss diagrams. Again, this is the longest, hardest assignment, but it will really help you plan your time accordingly. The truss exam question won't be as hard, but there will be one. It's not going to be anything like this. There will be 1, 2, 3, 4, only 4 elements in it. So a lot easier. And because it's Quercus, I have to walk you through it just a little bit. So stop, write down what you think is going to happen. Think about where the top chord is. Think about where the bottom chord is. Think about where the load is and what that means for the web elements. Maybe write down what you think on the piece of paper at the side, and then start doing the math. That's the best way I can think to test you on it without making it absolutely horrid for you. Next week is a little bit easier. The math gets a little bit simpler, and it's basically just building on what we've done this week with axial elements and making it for bending elements. So I'll see you next week. Don't curse me too much this week. We had to do it. It'll get better, I promise.